Hey, quick lesson here going through the chloride anomaly, and then also we're going to talk about the Hall-Heroult cell, which is for aluminum. So today's objective is to recognize that predicted reactions do not always occur. So the whole idea of this is what you've learned, it's not perfect. Sometimes things work out differently than we expect based on the theory that we learn. And one of those things is the chloride anomaly, which you're going to learn about today. Quick little thing, this is a small detail, but still important to realize again that the theory you're learning doesn't always give us the correct results in terms of what we observe when we do experiments. So for the chloride anomaly, in the electrolysis of aqueous chloride compounds, chlorine gas is produced instead of oxygen when chloride and water are the only reducing agents present, despite what the redox table says. So what do I mean by that? I'm just going to get my pen going here. What I mean by that is that if I have water and chloride as the only SRAs that I have, so chloride being right here and water being right here, well, as an RA, water should be the strongest reducing agent because it's lower on the right-hand side than chloride is. However, this is the reaction that actually occurs if, again, the strongest reducing agents that I have are water and chloride. This is actually the oxidation that happens, okay, at the anode instead of water making oxygen and hydrogen ion. So it's interesting that we get this instead of this. So let's kind of show what would happen here by going through a reaction and showing what would take place. So let's say we were looking at the electrolysis of sodium chloride aqueous. And this would be something that would be an obvious choice if you wanted to get hydrogen gas from water right through the electrolysis of waters. You might think, okay, well, I need an electrolyte in there. Let's just put some salt in and see what happens. But the problem with this is if you just put salt in as the ionic compound to make an electrolyte, and then you put current through it in order to get the hydrogen gas and to split apart water into hydrogen and oxygen, you don't actually get the oxygen gas, but instead what you get is you get chlorine gas being produced, which is of course very dangerous, right? Chlorine gas is poisonous. So let's work through what our major entities would be and then go through the motions of building this cell, because I think it's interesting to show how this would work as an electrolytic cell. And normally for the electrolysis of water, right, with the Hoffman apparatus that splits apart water into hydrogen and oxygen, what we use as an electrolyte is actually sodium sulfate, because then we get away from the chloride anomaly. The sodium is fine. The sodium ion is okay. It's the anion that we can't have chloride present, but we can have something like sulfates, and that is not a stronger reducing agent than water. So I have sodium ion, I have chloride ion, and I've got water, and I have my daughter tapping on my shoulder. So these are the major entities that I have. So if I go to my redox table, here's what I have for stuff. I have on the OA side, the first thing that I come to is the water. I don't have anything else except for sodium ion, which is way down here. That's not going to get reduced. So this is my reduction half reaction. So let's go ahead and write that out, might as well. So my RHR, my reduction half reaction, is going to be 2H2O liquid plus 2 electrons gives me, and I have the hydrogen gas, H2 gas, which is what I, probably want to get from the electrolysis of water, H2 gas, and 2OH minus aqueous. So that's my reduction half reaction. For my oxidation half reaction, this is where it gets interesting, because even though this is my SOA, when I look at the strongest reducing agent going from the bottom right up, you would think it would be water. This is the first thing you come to, but it turns out that this is actually what ends up going through the reaction. The chloride ends up being the thing that gets oxidized. So this is a chloride anomaly. We don't expect it to be this, the chloride, based on what we know. We expect it to be the water, but it actually is the chloride that ends up getting oxidized. So that is going to be my oxidation half reaction. In other words, the chloride is my SRA. So I end up with 2Cl minus aqueous which gives me 2 electrons and Cl2 gas. Okay, so if I build this cell and kind of go with what's happening here, my cathode, because of panic, is going to be negative. Well, my anode, which is not showing up on the diagram here because my face is in the way, is going to be the positive side. Doesn't matter what I use for an electrode for this, so why don't we just go with the plain old carbon, because that's always a good inert electrode to use. So again, this is positive going to my anode, and then negative going to my cathode. So at the cathode, what's going to happen is my reduction. So I'm going to have 2 waters coming to the electrode here, and it will react, having 2 electrons go up towards the anode. And then from this, I'm going to have H2 gas being produced. And then I'll also have the 2 hydroxides being made as well. So I would expect in my cathode that I would actually have these little bubbles of hydrogen coming up from there from the hydrogen gas being produced. Well, at the other side, at the anode side, what I would end up having is these 2 Cl minus aqueous, and I drew these electrons the wrong way. I'm sorry. This should be going in because, of course, at the cathode I have reduction. Then I have 2 chlorides that are coming to the anode. It's losing 2 electrons, so here's where my 2 electrons leave. And then I'm going to get Cl2 gas produced, right? As this leaves the 2 electrons going to the cathode, and then I have chlorine gas being produced at the anode. Electrons are traveling from anode to cathode in this direction. And then, of course, I have my anions, which would be Cl minus, migrating towards the anode. And then I have my cations, which, what do we have? Just sodium, Na positive aqueous, would be migrating towards the cathode. I should also mention that we would have hydroxide ions as well as my anion that is floating towards the anode or migrating in that direction as well as part of the internal circuit. But we don't have to be specific. We can even just say for this that we have anions moving to the anode and we have cations, and yes, it is sodium in this case, but just generally cations that would be moving towards the cathode. So again, what the chloride anomaly tells us is that we don't have water as our strongest reducing agent over here. Instead, it's the chloride ion that ends up turning to chlorine gas. And I'll say it again, this is only the case when my 2 strongest reducing agents are water and chloride. That's when this happens. And it's not what should be predicted. It's not what we think is going to happen based on the table, but that is what happens. Okay, moving forward, the other thing I want to talk about today was the Hall-Heroult cell. This is just a neat application, kind of a little bit of history and stuff to go along with this, of how aluminum, something that's incredibly common as a metal, used to be actually like this precious metal because it was so hard to get out of ore. So how can metals be recovered from ore as water is a stronger oxidizing agent than metal? So if I take a look at many metals, it's not all metals, but many metals, I have water right here, right, as an SOA, and then all of the ions for aluminum, magnesium, sodium, calcium, barium, potassium, lithium, they're below that. So I can't have those be the strongest oxidizing agent. So how can I reduce those in order to get the pure metal from ore? And the answer is we got to get rid of the water. So what we do is we actually deal with then molten ore, molten compounds, in order to get the reduction of that ion to take place so I can get a pure metal. Now, aluminum is really tough to do this with because of the fact that it has such a high melting point for aluminum oxide, the most common compound that aluminum is in. So aluminum oxide has this melting point of 2072 degrees Celsius. To get that temperature, incredibly difficult, incredibly expensive. It's tough to get there. So aluminum used to actually be this like precious metal. They used to build these statues out of aluminum, and it was like, oh my goodness, it's aluminum, because it was incredibly expensive. So it used to be that it was $45,000 in 1855 for a kilogram of aluminum. I mean, that's nothing, right? In terms of like a metal, having a kilogram of it. It changed the price from $45,000 to only 90 cents, and that's it. Okay, so the technology that allowed it to become so cheap is that they discovered that aluminum oxide actually dissolves really well in molten cryolite, which is Na3AlF6. So if you take this compound, you can melt that at around 1,000 degrees Celsius, and then the aluminum oxide will actually then dissolve in that. And then you have these aluminum ions floating around where aluminum is the strongest oxidizing agent present. The only other thing I have present is sodium ion, which if you take a look at our table is below aluminum, right? Aluminum is here, sodium ion is here. So aluminum becomes our strongest oxidizing agent, and then we're able to reduce it in order to get pure aluminum. So made it incredibly cheap. So here's a diagram of a Hall-Heroult cell, and how this works is they actually have this carbon anode where oxygen gets produced from the cryolite and from the aluminum oxide. So these oxygen ions, oxide ions, I should say, floating around that then get oxidized to make oxygen gas. So the oxygen gas bubbles out, and then the reduction of the aluminum ion happens at the cathode, which is basically this graphite lining all the way around, and then the iron cathode. So this conducts electrons to the aluminum ions. I then get liquid aluminum that sinks to the bottom of this, and then I can just drain it out, right? And this is all at 1,000 degrees Celsius or above. And then I can just drain out the aluminum as a molten aluminum from the bottom of this cell. So really neat, really efficient, and the temperature of this at just 1,000 degrees Celsius is very easy to obtain. So again, it made aluminum a widespread metal that was very cheap to produce from aluminum oxide by dissolving it in that molten cryolite. So it's just kind of a famous, neat cell, just a little bit of an application of electrolytic cells. If you're interested in seeing this process, take a look at a YouTube video that just is like Hall-Heroult cell or aluminum production. Kind of neat to see. All right, that's it for today.